Hello, everyone, and welcome to another wonderful day of chemistry. So today we finally get to talk about heats of reaction. However, the reason why it took us so long to talk about the heat generated by chemical reactions is because they're typically determined using calorimetry. Specifically, one of the more common methods of trying to determine the heat of a reaction is using what's called a bomb calorimeter. So in this case, what you do is you end up loading a sample of interest inside a enclosed steel container inside essentially a jacket full of water. That way, any energy either consumed or produced by the reaction will end up causing the temperature of the water to increase or decrease. By measuring the change in temperature of the water, you can then figure out exactly how much heat was generated or consumed by the reaction. Most typically, a bomb calorimeter is used by loading the system of interest and a whole bunch of oxygen. Then you do a combustion reaction which is initiated by having electricity enter the system. The reason it is called a bomb calorimeter is because the system is isochoric, that is constant volume. You're doing a combustion reaction, it generates a lot of high temperature gas, which means the system is now under high pressures. And in the early days of bomb calorimeters, where they weren't always built reliably, they could go off like a bomb. It is worth noting that bomb calorimeters can be used for other things than combustion reactions, but combustion reactions are one of the more reliable ways of determining a heat of reaction. And this can be demonstrated if we're looking one of the other unfortunate parts, though, is when we're looking at these heat of reactions, what we're specifically looking at is the internal energy of reaction, not the enthalpy. And that is a little bit tricky. So one of the things we can do is convert those internal energies of reaction to the much more useful in everyday life enthalpies of reaction. And we can really demonstrate this by assuming somebody performed a combustion reaction for sucrose. So by measuring the change in temperature, they were able to figure out exactly how much energy was produced by this reaction. Then what you can do is using this internal energy of reaction, you can relate it to the enthalpy using classic enthalpy equals internal energy plus the change in PV. Now, what we can do here is make note that in this reaction, our sucrose or table sugar isn't going to be changing pressure or volume that much, nor is our water. Most of the difference in pressure and volume is going to take place from the gases. So typically we go ahead and replace PV with nRT, because again, this is going to be responsible for most of the PV change. In this case, we're expecting temperature to be relatively constant. Ideal gas constant is a constant. So most of the change here is coming from the change in the number of moles of gas. So we have to look at how many moles of gas are being consumed, how many are produced. This is actually a rather nice case, as we're seeing that we're consuming 12 moles of gas, we're producing 12 moles of gas. So in this case, change in number of moles of gas is 0. But you can see from this principle that it might not always be 0. And so you should pay very close attention to your reaction. Am I consuming gas? Am I generating gas? And how will that influence my heat of reaction? Will it be higher or lower than I would expect? So as a result of this being one of those few cases where we're not changing the number of moles of gas, we're going to tend to see that the enthalpy of combustion is going to be the same as the internal energy of combustion. And I do want to emphasize that in general, if you're not consuming or producing aqueous or gas-phase species, don't expect the PV term to come into real big play, and internal energy and enthalpy are fairly similar. This is going to be less so for gas-phase species, as we see here, or aqueous species, as we'll talk about as we close out the chapter. So let's go ahead and see how we can use our enthalpies of reaction. So let's go ahead and say that I want to warm up some water by combusting some sucrose. So turns out you actually can set table sugar on fire. So I want to figure out how warm I can heat 100 grams or 100 milliliters of 25 degrees Celsius water just by combusting 1 gram of sucrose. So again, this is pretty much about a teaspoon of sugar. So if we go ahead and do this reaction, what we can do is set up the amount of heat generated by the reaction is going to be equal to the negative of the change in the heat of the water. Because again, these two substances will be in contrast. We can first start by determining the moles of sucrose combusted. So again, we can do this using the molecular weight of sucrose. Now, next, I know the enthalpy of combustion of sugar. That means the only thing I need left is the heat capacity of water, which we know, the mass of water, which we know, 100 grams, and then I can solve for the change in temperature. So we set up by solving for the change in temperature, dividing both sides by negative mass of water, heat capacity of water, plug in all of our numbers, and we find out that we heat the water by almost 40 degrees C. And I do want to actually emphasize this. By burning a teaspoon of sugar, or less than a teaspoon of sugar, you can heat 100 mils of water by 40 degrees. That is a lot of energy trapped in our food. And I do want to emphasize that when you're trying to figure out exactly how many calories are in a given food item, guess how they do it? They usually first dehydrate the food and then set it on fire and figure out how much water it can heat up. That's the origin of calorie. It's literally how much energy it takes to heat 1 gram of water 1 degree C. However, it is worth noting that food calories are 1 kilocal. So how much energy or how much you could heat 1 kilogram of water 1 degree C. So using our change in temperature, we can then add it to our initial temperature and figure out that you heat water to a nice crisp 64 degrees C, warm enough you can touch it, hot enough you shouldn't. So next time, we're going to see how you can use all of these various enthalpies of reaction for reactions that we know to figure out reactions that we don't. Next time, it's Hess's law. Until then, take care.